Can I have everyone's attention, please? Welcome to the student seminar this Monday. Today we have Lukas here, who's going to talk about big data.
Yeah, thanks Claudia, and welcome everyone. I'm Lukas. I'm a PhD student here in the LSDS group, and my talk is going to be about big data processing, navigating a zoo of yellow elephants, sharks, and giraffes. So I thought as a first slide I put this because basically it doesn't mean anything, but it looks nice. And that's probably something a bit what people think about big data sometimes. I mean, big data, right, is a buzzword. Everyone does it, everyone says it, but I mean, what does it actually mean? So it's kind of a little bit like that slide. Of course it has some meaning because all these companies, right, they're big data. So to answer what it actually means, I put together a couple of definitions from a couple of people and see what they think about it. So the first one is, if you type big data into Google, that's what you get from Google definitions, and it says extremely large data sets that may be analyzed computationally to reveal patterns, trends, and associations, especially relating to human behavior and interaction. Well, that kind of makes sense, right? There's a lot of data, and what people want to make sense out of it, to analyze it, maybe give some user recommendations, analyze trends, and these kind of things. The second one, that's kind of the classic one. I mean, some CEO. He says, I'm happy to repeat the definition I've heard, used, and think appropriately defines the overall subject. I believe it's Forrester's definition of volume, velocity, variety, and variability. A lot of different data coming fast and in different structures. So that's kind of the classical 3, 4, 5 V's. I mean, it started with a 3 V's, then people put a 4th V, now they put a 5th V, but it's a couple of V's. But the point here is a lot of data, different data, unstructured data, coming fast. Then a third one is from a guy at Google saying big data means that cannot fit easily into a standard relational database. Bit pragmatic, bit short. I mean, I'm not sure if I would agree on that because Facebook has that distributed MySQL cluster, which is a relational database. It's a lot of data in there, so. But he might have a point still because people not usually use relational databases to handle that data. Another one that's a bit more like esoterical maybe. So it says big data, which started as a technological innovation in distributed computing, is now a cultural movement by which we continue to discover how humanity interacts with the world and each other at large scale. So like a cultural movement that might be a bit big for the term big data, but it also kind of makes sense because a lot of people doing it these days, most of the companies, it's important for them because otherwise they will get a disadvantage on the market. And well, in research is big too. I mean, everyone kind of is touching big data somehow in his research. So it might actually be movement. I'm not sure if I will call it like that, but he has a point. And the last one is, while big data is often large in size relative to the available tool set, big actually refers to being important. Scientists and engineers have long known that data is valuable, but now the rest of the world, including those in control of purse strings, understand the value that can be created from data. So he says big actually, well, it means size, but it also means important. Because, well, if you have a lot of data, but it's just sitting there and it's kind of meaningless, well, no one will care analyzing it or want to processing it or even store it. So big also refers to kind of important. So from these, you see that it's actually, well, it's a buzzword somehow, but it has different angles and different aspects that you could look at it. And all of these people kind of have a point. So it's not like a clear thing like big data is that or big data is that. It's a lot of different things and it means different stuff for people. And if you're interested, so most of these come from this website. So Berkeley, they did kind of a survey. They asked a couple of people, like CEOs from tech companies and stuff, what do you think is big data? And they gave them these definitions. So there are a couple more there if you're interested. Just search for what is big data, Berkeley. So just a couple of numbers. These are usually also what people give, right? So Facebook has a data warehouse. They say it's 300 petabyte. Well, that's a lot of data, right? And also they say we load 600 terabyte every day in that. Well, that's also a lot of data coming very fast. Google processes 40,000 search queries per second. And that's not searching on a little file on your computer. It's basically searching the internet. So that's a lot. Twitter, well, processes 500 million tweets every day. Right, these are all these kinds of numbers. Amazon Web Services, a bit more hardware side. Amazon's cloud service, is comprised of estimated, no one really knows, but estimated 500,000 servers. So this is a lot of stuff. There's a lot of data. There's a lot of infrastructure. Well-known people use it for science, analyze large-scale experiments. They use it to give you user recommendations on Facebook, on Amazon, when you buy stuff. They use it to analyze trends, to make business decisions, and so on and so forth. The problem is this is a lot of stuff. So how can we actually store and analyze that efficiently? So the answer is this. Another slide which doesn't have any meaning. It's basically a bunch of tools just put together. I really like collecting these logos and putting them on slides. It looks so pretty. So there's a lot of systems out there. And today what we're going to do in the talk is basically has two parts. So the first part is going to be basically explaining kind of the previous slide. So what tools exist? How do they work? For what can they be used? So I'm going to start a bit with MapReduce, just the basics, because when I was asked to give the talk, I thought it was to be more like a tutorial, kind of general style of talk. So I'm trying to give in the first part a bit of an overview, what systems are there and what's the idea, how they work for people. I mean, I guess everyone must have heard of MapReduce, but probably not everyone has used it. So that might be interesting. And then in the second part, I'm going to see how much time we still have left, and then I'm going to just quickly talk a bit about the work we're doing in LSDS group. It's called NetAg. It's a program of Middlebox, and we use also that to speed up big data processing. So let's start with part one and a bit of history. So how did all that stuff evolve? So first, people had mainframes and supercomputers, right? Mainframes, supercomputers, big, customized machines, a lot of processing power to compute computationally expensive jobs. Also very expensive machines, and the problem is, well, they cost a lot and they're very hard to scale. I mean, they still kind of exist, especially supercomputers, because scientists, they still have the requirement, well, I want to compute a differential equation with 1 million of parameters. I mean, what am I going to do? Well, run it on one of these things. However, for mid-size or large internet companies, this was not really the way to go, because their computation wasn't that expensive. They had a lot of data, but they don't want to compute a differential equation. They just, maybe the most complex is like a k-means or something like that, or just some, I don't know, just some select or some sum over or some data. So it shifted more to data-intensive computing, not that computational expensive computing. And because this custom hardware is so expensive, people started doing like COTS hardware-based data centers. So COTS is commodity off the shelf. That means, well, I go to Curry's, I buy a couple of servers, I put them in a rack, I'm done. Because that is a lot more scalable, that is a lot cheaper, and that's also what mid-sized companies can afford, for example. So it basically means cheap hardware, but a lot of it. And that shift to data-intensive computing made that kind of feasible. Once people did that, the problem was, okay, we now have a big cluster. We have 1,000 cheap machines connected together. How can we actually easily and reliably program them? Because if you have a lot of cheap machines, that means some of them are going to fail always. And the second point is you don't want to want an engineer spending half a year on programming a distributed k-means on like 1,000 machines. And that's where basically MapReduce came in. So MapReduce was originally, well, it was introduced by 2 engineers from Google, published at OSDI in 2004, the paper MapReduce Simplified Data Processing on Large Clusters. Now 12,000 citations, so quite impactful, I would say. And then following that, the open source implementation of MapReduce Hadoop. And the idea is pretty simple. So basically, what MapReduce does is provides you an abstract programming model that hides all the complexity of parallel programming. So really all of it. You don't have to do anything. The only thing you get is 2 functions, a map and a reduce. You implement those, and the rest is kind of done. The program is then going to be executed parallel automatically on your cluster. So how does that actually work? So as I said, you get 2 functions. It's a map function and a reduce function, and you see the signatures there. So the map basically reads from some input items from an input. It processes every item that can have some kind of type, and then it applies your function that you put in the map on every single item. And then it returns an output key value pair. And then you implement reduce. What reduce gets is a pair of a key and a list of values for the same key, and it takes those, it applies the function that you implement on this key value pair, and then it produces a final output. And that's really all you have to do. And then you can run it on 1,000 machines in parallel if you want. So let's look at word count as an example. So word count is a very famous example because it's very simple and is a really toy example, but it kind of gives you the idea what that stuff is actually supposed to do. So word count, when you run a word count job, your goal is to calculate the occurrence of every single word in a large document, in a book or whatever. And just want to count how many times does and occur, how many times does whatever occur, and so on and so forth. You might even use that for some Twitter feed analysis or something like that. So it does have some application, but it's still a pretty toy example. But it serves the purpose. So for word count, if we want to count the words in a large document, what we would do is we write these two functions, map and reduce. Map basically takes an input item, is a string. It splits it on spaces so that now you get an array of words, basically. And then it returns a key value pair, meaning word and one. For every word that you get, it's just word and count one, because once you see a word, its count is one, right? So you get the stream of key value pairs for every word. You emit a one, basically. And then for the reduce function, what you do, now you get you get a key and a list of counts now. So the list of counts now is already prepared for you by the framework. So you just get word and all the counts that the framework gives you. Well, and basically what you do, you iterate through these counts and sum them up. And that is your final result. And that's really all you have to do. So if you look on the right now, there's just a little sequential example. You have your input. We read from it this very meaningful sentence. This is this and this. And this input is fed to a mapper task. And the mapper basically runs the map function. So as we just saw, it will produce key value pair. So it will take every single word, produce the word plus a 1 as the output, and gives you a stream of key value pairs. So it gives you this one, this one, and so on and so forth. This is then fed to a shuffle operator. So that's already out of your control. That's all MapReduce framework. And what shuffle does is basically it's sorting your key value pairs, it's preparing your list of values, and then it's going to send them to your reducer or the reduce task. So what shuffle is going to produce is and one is one, and this with 3 ones because that sentence contains a 3 this. And then the reducer is going to basically run your reduce function, which produces the final output. So now what you got is you have 1 and, 1 is, and 3 this. And well, this is basically all. Now the cool thing is that you can really run that in parallel. So imagine, yeah.
Lucas, in your pseudocode for map, wouldn't that just return the first word rather than...
Forgive me, I mean, that's true. The return will return the function. I just wanted to make it kind of... You usually would iterate, and then you accumulate it somewhere, and then you return the whole thing. Or you write it to some output buffer, basically. So this return statement is not supposed to return for the first word. OK? Yeah. OK, so the cool thing is you can now run that automatically in parallel. So imagine you have a really large file you want to count words, and you cannot store that thing on a single machine because it's really big. So basically, you now store it at a couple of machines. So you partition it, store it at multiple machines, but you only write that single map and reduce. And then what the framework is going to do for you is it's going to run the mappers on the single partitions. It's going to feed it to the shuffle. The shuffle is going to do the sorting and so on. And then the shuffle is going to take care of sending the keys to the reducers. And now it's going to partition the output from the shuffle according to keys, just to make sure that the separate reducers, they end up with the same keys. So this one, for example, now gets all the words that start with an A to start with an E, and that one from F to J, and so on and so forth. And in the end, well, you get your result. All is run in parallel. You don't have to do anything. But that's not all. So this is basically how you program it. But the framework does even more for you. So one important point is that it is fault tolerant. So it takes care of fault tolerance. So I said before that in these commodity clusters, failure is really high. So a disk or a machine, they fail all the time. So you want to make sure you don't lose data. You don't want to restart your job all the time. So basically, the framework takes care for that of you. It executes tasks on different machines and recovers from failure and so on transparently. It also does scheduling. So you don't have to take care of where do I run the task, when do I run the tasks, how do they communicate with each other. That's all done by the framework. They do some smart stuff. They try to maximize data locality and then executes the task for you such that your resources are always, well, as good utilized as possible. They also do the message passing, so they send basically the data across their network, so you really just write these two functions. So that is pretty neat. And after that, there were a lot of extensions to MapReduce. So people thought, okay, what if I want to do SQL processing? And I don't want to buy a big Oracle mainframe. Can I do that with Hadoop? So there's the Apache Hive and the Apache Pig projects that basically put a query processing layer on top of Pig. Pig is some kind of scripting language. Hive gives you actual SQL, not complete full SQL, but most of the SQL operations you need. Then people also thought, what about machine learning? So there's the Mahout project, which gives you a machine learning library. You can do like k-means clustering, you can do naive Bayes classification, random forest, these kind of things. They're all implemented in Mahout, and underneath, they're translated into MapReduce jobs and then executed as a sequence of MapReduce jobs. There's also Apache Giraffe, which is then for graph processing. So if you have a big graph, you can use that tool, and then you can run a PageRank or an all-pair shortest path or whatever graph algorithm you want. It's translated into a MapReduce job, executed in parallel on your data. So that is nice. However, there's still drawbacks. The main drawback is that Hadoop, the MapReduce or the open source implementation Hadoop, that was more concentrated for batch processing. So long-running jobs on long data. So people didn't really care. Well, launching a job is pretty slow actually in Hadoop. Also launching a mapper, I mean, a mapper is actually in the Hadoop implementation, it's a separate JVM. I mean, that takes ages to launch. There's not a process, it's actually separate, well, it's a process, but it's a separate JVM that you have to launch and all that stuff. So this is really slow, but people didn't care about the overhead because they say, well, it's batch processing. Your job runs 2 hours, 2 days. Who cares about 10 seconds? So that's one problem if you want to do some more interactive stuff. The other problem is that it only provides you these two phases, only the map and the reduce phase. So that's pretty static. So you only get map and reduce. So if you want to do k-means iterative, where you have to iterate through a data set multiple times and compute some error and these kind of things, you can do that in MapReduce, but it's difficult and it's pretty hacky. Also for SQL, if you want to join two tables, you're basically reading from two input sources. You can do it in MapReduce, but it's hacky and it's not that efficient. So the point is, MapReduce has a lot of useful applications, but it's also inflexible for lots of other stuff. And that's when people started to think, how can we make it more flexible? And they came up with basically general data flow-based programming. So here you see, this is the MapReduce model. Map stage and a reduce stage, that's all you get. And then people started thinking, how can we make that more general? And they came up with basically a DAG abstraction to define your data flow. So a directed acyclic graph that gives you a flow-based API to do transformations on your data. So now you see you can, for example, do something like this. You have like a map, you feed that to two operators, you do a join, you could do another map, then you kind of split it somehow, you implement some reduce function, you shuffle the data, and then you implement some user-defined function, whatever you want. So this is a lot more flexible because iterations, for example, they're now just another stage in that DAG. And join, you see, you can easily read from different inputs and forward it to a single node. So basically, what you get, well, you get a DAG, a programmable DAG as an abstractions. Vertices in that DAG are programs that run transformations on your data, like map or reduce. Then the edges are communication channels, like shared memory, TCP, whatever, that moves your data through the stages. And then usually what systems that implement that give you is a set of predefined vertices. So they give you, for example, a map, which defines how many inputs and output that thing gonna have. There's also systems that let you define vertices like arbitrary with arbitrary inputs and outputs, but usually people are fine with a couple of operators, map, reduce, join, split, filter, and they can implement most of the stuff with it. And you're getting a lot more flexible and a lot more expressive by doing that. While you can still keep that kind of a flow-based model that MapReduce gives you. So DAG-based systems are here, the main one. So there's Dryad. Dryad was developed by Microsoft. I think it was, to my knowledge, is the earliest to propose that, or the most famous to propose it. It was published in Ulysses 2007. It's basically the DAG extraction, and it gives you a couple of predefined operators, but it also lets you implement your completely own vertices. Then there is Spark, which is, I think, probably the most famous one at the moment. It was developed by Berkeley. It kind of kicked off as a startup. These guys probably all going to be millionaires soon. We're still waiting for that. It's kind of the same approach, but Spark now what they do is they focus also on main memory computation. So they provide you this, it's called REDs, an abstraction, so that your data can be kept in memory all the time, and you can solely do distributed in-memory computation very, very easy. And then there's TESS. That is basically the data flow engine from the Hadoop community. You can see now the little yellow elephant got a lot more aggressive because TESS is supposed to be more flexible and also faster because it gets rid of all that overhead and decouples components. And then, so these are basically the base system, and there's now tons of systems on top of that. And these next two slides are just to give you a bit of an overview. Maybe some of you stumbled upon one of these systems at some point. You say, oh, what is actually that, or what does that actually mean, or what is this for again? When I started my PhD, people were throwing around with these systems like, yeah, and Dryad link, and actually there's this thing, and drill, and I don't know. And I was like, what the f? And I was struggling with getting all these things right. I mean, you can classify them kind of nicely, and this just to give you a bit of an overview of what is out there. So this is all just SQL and Hadoop. It's called SQL and Hadoop, but it's basically SQL processing on top of these data DAG engines. And you see that kind of Facebook has a system called Presto. Google has BigQuery, used to be called Dremel. IBM has BigSQL. There is a new Hive version developed by Hortonworks, which is called Stinger. Then there's Drill. Well, I don't know who started that, but it's some Apache project. That's kind of the same thing. There's from TU Berlin, there's the Flink project. There's Impala from Cloudera. 2 weeks ago, eBay released their own SQL and Hadoop processing system called Kylin. Then there's, Databricks is the company that's doing Spark now. There's also SQL on top of Spark. It used to be called Shark, that's why it's in the title, but now it's actually called Spark SQL. And there's also DryLink on top of Microsoft. So these are all the ones I know. There's probably more. The thing is, they all kind of do the same, but it's interesting to see because every company kind of has some different requirements, it seems. So they still do their own stuff. I mean, there's not a single system like back in the days when there was a DB2 and an Oracle and the SQL Server, and that's basically all, and they were just competing for market. These guys are not competing for market because eBay, they don't sell Kylin. They just had some small requirement somewhere that all of these systems couldn't fit. So they implemented their own stuff. And that's kind of interesting maybe for us to see that maybe there's something that needs some higher abstraction still that we can unify all of these. So yeah, these are just a couple of names. Then there's other systems. I just put for graph and stream processing. Now, I'm not an expert on these. I kind of just put them for completeness. So there's GraphX. This is graph processing on top of Spark. There's GraphLab from CMU. There's Pregel, which is a Google system that kind of is the baseline for Giraffe that we saw before. And there's some stream processing system like Twitter Storm, S4, Kafka from LinkedIn, and again, some stream processing on top of Spark. So all these systems, I mean, they have differences, but in general, they're used for the same stuff. So if you maybe stumble upon one of these in the future, maybe you have now a bit better idea what they stand for and what's behind them. And with that, I want to move to the second part. I mean, how much time we still have?
If you can finish by 35, that would be good.
7 minutes, awesome. That should be enough. So now I'm going to explain a bit about NetAct. That's the work we were doing in LSTS. So in that we were looking at data center networks, and they look like this. But that's not something we can work with. So we kind of abstract them a little bit more, and then they look like this. So a data center network is basically a couple of racks with servers. Then you have a top of rack switch that connects all the servers. Then you have access switches on a higher layer, and you have a couple of core routers that connect all the racks in different subnets to each other. So that's basically how a data center works. And in these kind of things, people now want to run their Hadoop, their Pregel, their Shark, or whatever. Now the problem, or one of the problems with these is that the network can be a problem. Because you have distributed computation, right? You have a lot of machines involved. So we saw in Hadoop there's a shuffle phase, for example. So machines send a lot of data in between each other. And there's basically two major problems. The first one is a scarce edge bandwidth. So imagine you have a search engine front end, you submit a query, and then the query is dispatched to a couple of backends. And then on your partition data is searched in parallel. Now once your backends get the result, they send all the result back to the front end. And this is like a many-to-one traffic, and the problem is, well, the front end, the network connection to the front end gets kind of overloaded. You might get congestion, you might lose packets. You definitely waste resources because basically the senders will have to be slowed down at some point. So they cannot send at their full speed. The other problem is that in a data center, the links between the higher layers, for example, top of rack and an access switch, they're usually oversubscribed to save some money. So if you look at this, we have 6 servers here. Maybe they have all 1 gigabit, so basically you can get a rate of 6 gigabit at that switch. But to save money, this link is also only just 1 gigabit. So you see what happens when all these servers send something out. For example, during MapReduce shuffle, this link will become a bottleneck. And the same for the other rack. And once you move up into the core of the network, this will become a problem. And this will slow down jobs and it will waste resources. So what we observed was that these kind of systems, MapReduce or distributed search engines, they usually have this n-to-1 traffic pattern. And what they do is, at the destination, they somehow aggregate this data, combine it to some final result. As we also saw before with the Hadoop word count, right? You can take all these integers, you compute a sum over them, and that's your final result. And we also observed that these aggregation functions, they are often associative and commutative. And that is a cool thing because this allows us to do early aggregation of partial results. So that means you don't need all the results to compute an aggregate. You can already compute the aggregate on a subset of the results without changing the final result. And the idea is now to do this partial aggregation in the network. So if we consider again some, let's say, mappers send their word counts somewhere, and then this top of the rack switch is the first point where all these flows from the mappers meet first. So now you got already a subset of data combined there, so you could aggregate on that switch. And now if you aggregate 6 integers to a single integer, you see what you send out is a lot less than you had before. And the same for the other rack, and you can do that again as you move to the core of the network. The question now was, how can we do that? I mean, if you're a MapReduce developer and you want to program map and reduce, that's fine, but you don't want to program a programmable switch, some aggregation function on a switch. That is too much, and that is going to take long, and that is not good. So we thought we will do a middle box approach, so that basically means we take a server, we connect it to every switch with a high bandwidth link, so that this link won't become the bottleneck, and then we reroute the traffic through this middle box. And the middle box then aggregates. So an example, I guess, will make that pretty clear. So this is now a subset of the network. We got a couple of machines. They send out, well, their counts, and then we reroute it via that high bandwidth link to what we call network box. And the box computes a sum, 17. And then you see the 4 integers are now reduced to a single one. This is less space, and we can save bandwidth, and the oversubscribed link is now relieved. And this is a better solution because you only need one high bandwidth link. If you upgrade your data center to more bandwidth, that's fine, but that's very expensive. So with our solution, basically, you just need a couple servers, you need a couple of high bandwidth links, but then that's fine. And you can speed up your results and well, fully utilize your resources because you don't want to waste resources. That's basically the point. Okay, so that's basically all. To conclude, what we saw is that big data is a buzzword, and well, that big data has many challenges and definitions. The challenges are kind of interesting. So it's not only a buzzword. I think that's maybe one point that's important. It's not only it's a buzzword used by a lot of people, but there's interesting stuff, and I think that is proved by the research that is done on these kind of systems. So there is MapReduce. There are a lot of other existing tools. I hope you could get like a bit of an overview on what is out there. what you can use and what you can do with these tools. And then in the end, what we saw, our contribution to the big data world, that programmable middle box that does some in-network aggregation to save some bandwidth. Okay, and that is all from my side. Thank you very much.
I think we can have one question, if someone has a question.
Can't we do a distributed aggregation on the cluster instead of putting a new cluster?
So
Or just one of the nodes gets the role of the net aggregator in the cluster?
this is something you can do, and this is also what systems did before. However, we were also trying that. We were doing some evaluation on that. The problem you get is once your traffic hits the core of the network, then there's no aggregation you can do. You can only do edge-based aggregation. But for example, the stuff that comes from this rack and the stuff that comes from this rack, you can only do these aggregations, right?
Yes.
You don't get that benefit anymore. So that's kind of a benefit from our solution. You can do it everywhere in the network.
Okay. I'm sure Lukas is very happy to answer more questions while we're having some lunch. So whoever gets to the trolley first, take the food down onto that table, then we have more space here, and then Lukas can still answer questions. So let's maybe thank him again.
Nice presentation.
Thanks.